Right. So on your model, the inner core, according to all the documents I've found, clearly states on all of them solid.
Correct.
So when we look at the melting point in Celsius,
Yeah, and the boiling, it's over the boiling point. I know.
yeah, but it's over it by what 7,200 degrees Celsius. So call it. Let's round it down to 5,000 for easy maths. It's more than double, isn't it? It's like huge amounts more.
Yeah, it's approximately 3 times. Yeah.
How can something exist as a solid when the boiling point has gone beyond itself significantly?
Do you understand that the boiling point of something is dependent on the outside pressure of it?
It doesn't say that. It says the boiling point is 2,800 degrees.
Yeah, and when you look for boiling point, there's always a standard boiling point, meaning at 1 atmosphere of pressure.
At this point, I agree with you.
All right, so do you agree that we can extrapolate that into the other direction? Then do me a favor and look up phase diagram for iron. There we go, that one is nice. So, do you see... So you say... yeah, that one is great, pure iron phase diagram. At the bottom you have the axis with the pressure, right?
Sure.
All right, so go to an x value of 1 bar.
Okay.
And now go up until you reach the line between vapor and liquid.
Yeah.
It's like 2,800 or something.
Okay.
All right. Wasn't your evaporation temperature of iron in the source that you showed before at 2,800 degrees?
Boiling point 2,800.
Yes, that's the evaporation. That's the boiling point. Okay. Now look at the slope.
Hang on. What point did I get that right then? That was the point where the liquid changes to the vapor. 2,800. It was right. Correct.
Yes, but only at that pressure.
Okay.
Okay. Do you see that the further right you go into the so look at the slope of the curve between the vapor phase and the liquid phase.
Yes.
The line between vapor and liquid. Yeah, that one. See how that is sloping?
Yeah, it's quite a steep angle. Yes.
Yes. See how when you go to 100 bars?
Yes.
That in this diagram, at least at these temperatures, it will always stay liquid.
Yeah. Okay, I get that.
Okay.
But then the question becomes: can you prove what the pressure of the Earth is inside the Earth?
Yes.
How?
First of all, up to a certain depth, we can actually measure it directly. On the bottom of the ocean, it's over 1,000 bars. That's why it's so hard to reach it.
Yeah, but that's on the bottom of the ocean, though. We're talking inside the Earth.
Yeah, you can start drilling holes.
Right, and we know the deepest hole in the Earth they've ever did
15
was like
kilometers or something.
Yeah, the Kola Bore mine in North Russia, and that was only 8 miles.
Yes. But the pressure at that depth is already over 100 bars.
How do you know? Have you got any evidence for that?
Yeah, just do me a favor and look for Challenger Deep.
What was that word?
Challenger Deep.
I'm sorry, you'll have to spell that. Is
Challenger.
it
Challenger.
Challenger?
Deep. DEEP.
Challenger Deep.
All right. Go to the wiki page. Just search for pressure.
Yeah, but we're not doing pressure of water. We're doing pressure inside the hole. You said inside the hole the pressure was already such. Whatever it was that you said.
Yes, but it's easier to demonstrate with water.
No, but I asked you specifically for the pressure inside the hole, and you gave me water. That's not what I asked for.
Then look for deepest boring hole or something.
Well, the deepest borehole is the Kola Bore mine. Shouldn't we be looking at that?
Yeah, maybe.
Right, so deepest drilled hole should be the Kola Bore mine. Kola super deep borehole consists of several holes. Right, this is where you'll find the pressure if it's in there. So in answer to the question, can you prove what the pressure is down there? Let's find if there's a Wikipedia page. Right, so I'm going to type search on the page for the word pressure. Is that okay?
Yeah, sure.
So where's the search button gone?
Control F.
Pressure. Nothing. Oh, you've got no evidence for that assertion, then, have you?
Maybe if it isn't in this wiki article, it's somewhere else.
You can't claim it as a fact if you can't prove it. So there's nothing.
How's it called? The Kola borehole, right?
The Kola super deep borehole. You claim that the pressure was already above 100. So what's the evidence for that? Because I would think that the pressure.
Do you agree that if the deepest part of the Mariana Trench, which is Challenger Deep, yes, water is lighter. It has less density than rock. Do you know that?
Right, we're talking about the pressure inside the hole.
Yes.
I asked you for
yes.
evidence.
Yes. No. Yeah. Stop.
Right. The point we're trying to prove is what pressure is the iron inside the Earth. Because
Yes.
you were talking about this. Where was the one? This one. And your point was, where's it gone? As the pressure goes up, then the temperature goes up with it. Okay, I accept that. However, I'm asking you to prove.
Actually, no. Not the temperature goes up with it. The vapor temperature will go up with it.
Yeah, the point where it becomes from a liquid to a vapor, that goes up exponentially with the pressure.
Correct. But you can see that already at 10. Just look at 10 bars, right?
Yeah, but hang on. I accept it. I accept your point. That's not indisputable. What I'm asking is, what pressure is inside the Earth, and how do you know?
As said, with the deep boreholes, I just have to look it up. Give me a second.
Okay, take your time.
I'm not finding a value right now, but we could calculate it.
Well, we can demonstrate it.
You can demonstrate it, or what are you talking about?
Well, we can demonstrate the pressure of the Earth. Every volcanic eruption I've ever seen has been generally not that powerful. It runs slowly over the mountain.
Not that powerful, yeah, but first of all, the volcanic eruptions don't directly come from the Earth's center. They are in the mantle that's only a few kilometers under you.
Exactly. So what pressure would you reasonably expect there to be under in the what you call the center of the Earth?
You can calculate it.
Which is, well, you can calculate it, but can you prove it? Because if you can't prove it, I mean, I would argue that the pressure here is...
Yeah, it's an extrapolation. For example,
exactly.
we know... No, first, yeah, stop. Let's start with something simple, all right?
Hang on. An extrapolation is not evidence. It's a calculation.
Calculations are evidence. We can use them.
They're a calculation.
Yes. For example, we know that when water... when you're 6 meters, 7 meters... I would have to calculate it. The further deeper you go in water, the higher the pressure, right?
Agreed, but I'm not asking about...
And we can calculate that. Only knowing the depth of the water, we can calculate the outside pressure. And it's the same with rock. The only thing we need to know is how much does the rock over you weigh? And how high is the column of rock that is over you to calculate the pressure?
Alex, here's a visual...
equally valid.
Here's a good visual representation. You see my screen, yeah?
Yes.
Right, at the moment this erupts, the pressure is a lot higher than when it's settled down. Agreed?
The pressure is a lot higher.
As it's erupting?
No. The pressure on the magnet chamber is, or whatever is feeding the volcano, is identical all the time. The only difference is that the plug, or however this blockade that is stopping the magma from coming, or the smoke from coming out, is no longer strong enough to hold it.
Exactly. So at the moment of eruption, the pressure is high. So what your graph is going to show...
No. The pressure is identical to before.
So, all right. So in that case, then it doesn't make any difference about the strength of the eruption. What matters is that there's an eruption, and then we can basically conclude there is some pressure. But arguably, given that most eruptions are not that aggressive, most, not all, but most, the pressure is minuscule. It's not that much compared to like the Earth that we're on. But let's say that you are correct. Let's say that we'll go with your water. What's the pressure? What's the pressure in the ocean 2 miles deep compared to 2 miles inside a drilled hole?
The pressure inside a drilled hole, first of all, as said, it will be a little bit dependent on which rock is on top of it. Well, let's not go with hole. We are in the middle of the rock, right? There's rock over us.
Yeah, but we're trying to prove the pressure inside the Earth. So to do that, how do we do that?
So you can't do it with atmosphere above you.
Exactly. So how else can you do it?
By applying a pressure plate.
Go on.
First of all, again, we can calculate how much, if we know how much weight or how much rock is above you, we can calculate the pressure. It's only the force that is applied by it. Yeah,
but I want you to show evidence of what the pressure is, not a calculation of pressure. I want to show.
All right, again, let's go to water because it's much easier. In the challenge at 10 or 11 kilometers depth, we have about 1,000 bars of pressure. the density of rock is about 3 or 4 times that of water. Therefore, we should have
You're a loser.
3 or 4,000 bars. Continuing, if you extrapolate that, we end up with Earth core pressure, inner core temperature and pressure. Since you like using Wikipedia,
I don't. I hate using it.
then why do you use it all the time?
That's what you guys do.
No, I would actually. First of all, I probably start with what the fuck are you typing there?
I'll see if you're watching.
Can you see my screen again?
Well, hang on. Are we still on the pressure of the Earth point?
Yes.
Can I see your screen? Let's have a look.
You should be able to. Alright, so I just googled for inner Earth core. What I would do now, first of all, I checked, yeah, the values you were given were right, 5,700. Oh, was it Kelvin?
Celsius I was using.
4,400 Celsius, 700 Kelvin, yeah. Pressure, 330 gigapascal. If you have to calculate that or convert that to bars, that's no problem, you can do that. What I would do now is take a look at the source.
Stop. Before you do, let's just put this in context. Go back to that bit there. It says, the temperature of the inner core can be estimated, and I'm asking for proof here, not estimations, but nonetheless, can be estimated by considering both the theoretical and the experimentally demonstrated constraints on the melting. Alex, this is total conjecture.
No, it isn't.
It is.
No.
There's 3 words there that none of it are. It says estimated by theoretical and experimentally demonstrated constraints.
Yes, experimentally demonstrated.
Yeah, none of these. This isn't empirical. This is pseudoscience.
No, it is empirical.
It's not. It's estimations.
Yes. No, taking experiments is literally not. It literally is.
Yeah, but it's theoretical, Alex. It says theoretical, and it says
experimental. As soon as you start doing experiments, it's empirical.
Yeah, but it's pseudo. No. It's not empirical when it's based on theory. It's theoretical.
But Alex. It's based on evidence, on experiments.
Yeah, experiments that are theoretical. I'm asking for the evidence.
No. Theoretical means that you start calculating it based on extrapolations, for example. Alex. And then you can check that with the experiment. That's why I'm trying to go to the source.
Alex, can I just check what this has got to do with magnetism?
So this is the source that Wikipedia is citing. Alright? It's shown... I would need a geologist for this. Is Purple Dan here? So again, going back to the estimation. Even if you agree it's just an estimation. I agree it's just an estimation. But it's the best it's the best that we have.
There you go. So let's go back to the content that you were talking about with the...
No, I want to continue this. 330...
What's the point? It's not based on evidence or empirical stuff. It's based on pseudoscience. That's all it is.
It's the best we have. It's the best experiments we have.
It's not evidence, though, and that's not acceptable. If that's the best that's not acceptable.
Even if our knowledge is incomplete, we still have a pretty damn good clue about it, and we can make approximations about it. Even if it's not completely accurate, we can use that value and we can at least show how much those 330 gigapascals is on that phase diagram.
You can't prove. That's the point. You can't demonstrate what the pressure is of the Earth to apply that phase dynamics or whatever it was. What was the thing that we were showing before?
Let's calculate this in bar. 330 gigapascals. Ooh.
Right, Alex, we're at the point where I've asked you to prove the pressure so that we can apply the iron phase diagram, and we're unable to do it because you've not been able to prove the pressure other than theory. Theory's not proven.
Agreed, it's not proven, but it's the best approximation that we can do.
That's not acceptable.
It is acceptable.
Well, to you it might be, as a theoretical scientist, maybe, but to somebody
I'm not a theoretical scientist. I'm actually a lab scientist. I'm cooking stuff.
Well, whatever. What I'm saying is theory is not acceptable as evidence because it isn't
not a theory if it's experimentally at least hinted.
Father Christmas is a theory.
No, it's a hypothesis and it doesn't work.
Father Christmas is a hypothesis?
Yes.
Father Christmas is a theoretical being that doesn't exist?
Yes, and it's at least a hypothesis to explain something, but when you take a look at it, you can show that it's unlikely or impossible to be factual.
So, Alex, we're still at the point where you can't prove the pressure, therefore you can't prove the boiling temperature of iron. You can't have conjecture. You can't have hypothetical.
Let's do it the other way around.
Go on.
So, can you please go back to the phase diagram? Oh, you still have it, right?
Yeah, I'm still on it. Yeah.
All right. So, when you extrapolate this, let's just say that that this diagram continues to 5,500 degrees. Okay.
Yeah.
You would expect the slope of the curve between vapor and liquid to be at about at 5,000 degrees, maybe at about 50 or so bars. Let's just say 100. Let's just say 1,000 bars. Fuck it.
It's going to be about 3 bars, isn't it?
No, I think it's more, and you have to take a look at the scale that is logarithmic.
Yeah, but the point is, it's not a lot more than 1.
Yeah, whatever. Now compare that to the actual estimation on how high the pressure inside the Earth's core is at.
Hang on, compare it to
3.3 million bars.
No, you can't do it to a hypothetical. It's either you know the value or you don't. If you're going to hypothesize,
if it's the best estimation that we have, just compare how huge the difference is. I mean, if you're saying that at 3 bars,
Alex, how does this relate to the magnetism of the core?
It relates to you started with the fact that you said it's well over the boiling temperature, right? That was what you were starting with.
Yes, that's what I said. So let me go back to it. I said the boiling point is 2,800. So what you've got to try and do is get that pressure up to justify the claim that it isn't going to get to the boiling point. Or actually, no, because the Curie point is only 769 degrees. So that's the point where
the Curie point is irrelevant.
No, it's very relevant because that's the point where it loses its magnetism. Agreed?
Do you know the Curie point of other metals?
How is it relevant?
That's just a question. Do you know Curie points of other metals?
Right, I can look them up very easily. Would you like me to look up a particular metal? Can we not stick to the iron because that's what the core's made of?
Yeah, all right. So the Curie temperature in Celsius is...
Hang on. It's 769 Celsius, but let's go back to the point...
1043 Kelvin, yeah, all right.
700 degrees Celsius. So according to this, iron will turn into a vapor at 10 to the power 12 or less of pressure. So it will be
in bars, that's literally a vacuum.
Yeah, so that's a negative value, right?
No, a value is never negative. This is still a positive value, only a relatively small one.
So basically the pressure is going to be... So the only way that can do this, according to this, is in pretty much near a vacuum. Is that right?
Why would you want to have it in vapor, in the vapor phase?
Because once it goes beyond... all right, the Curie point. So the boiling point. Yeah, okay, let's stick with the Curie point. The reality
go further to the right. If you have a bigger pressure, you're still under the Curie point and you're at a solid.
Yeah, but
that's what we're at. We're below the Curie point, and we are in an environment that has enough pressure to have it as a solid.
What do you mean we're below the Curie point? We're not. We're way above it. Look,
no, currently here, we on the surface of the planet, take an iron nail. We're below the Curie point.
Yeah, but that's irrelevant. The point is the core's supposed to be 7,200 degrees C.
Yes.
So that's like 10 times the value that the Curie point is. So where's again? You have to prove the pressure, which we've already established that you can't do. So it's hypothetical. So the reality is, if the core's at the temperature that they say it is, the Curie temperature's been met, and look what it says. At temperatures below the Curie point, the magnetic moments are completely aligned with the magnetic domains in the ferromagnets.
Yeah, that's correct. That's how the Curie temperature is defined.
So what happens above it?
You can't magnetize it anymore, but you can still have.
That's not true.
Yes, you can still have magnetic fields, inducted magnetic fields.
Correct, but where do they come from in the Earth model?
We have demonstrated with models. You can still have non-ferromagnetic fluids that produce magnetic fields as soon as there's a force acting on them.
Right, let's start at the beginning because I want the people in chat to see this because I want you to... You're literally going to Curie temperature. I want you to correct me with where I go wrong here, okay? Because I'm stupid, I'm a baller, I don't know what I'm talking about. the Curie temperature, right, is the temperature at which certain materials lose their permanent magnetic properties to be replaced by induced magnetism, right?
Correct.
Agreed. So when you click induced magnetism, it says, let me find it, net magnetization results from the response of a material, in this case the iron core, to an external magnetic field. So unless it gets an external magnetic field, it isn't going to be magnetized. So where's the magnetic field?
Net magnetism from the response of a material to an external magnetic field.
So can you tell me on your model?
Wait, stop. The sentence continued.
Together with
any unbalanced magnetic dipole moments that may be inherent in the material itself, for example, in ferromagnets.
Yeah. So could you tell me where either of them to apply in this example?
Yeah, you have movements inside the planet.
Agreed. But the movements are based on what? The convection currents, essentially, right?
Yeah, for example, and also the rotation of the planet.
Yeah, sure. Coriolis force. Yeah, I get it. But if you need a lot of power, a lot of energy to keep that core at 10. Oh, was it 7,000 degrees? It's going to create convection currents, yes, and that will add to it, yes. However, it's not going to be the cause of it. Something has to feed that. Otherwise, it's going to be a perpetual motion machine.
No. First of all, magnetic field. No. First of all, what is feeding this is the rotation of the planet directly.
No, are you joking? It moves so slow that nobody can tell it.
So what?
Can you prove that point to be true? I'm saying that's bullshit. Can you prove that the rotation...
We've done model experiments of this.
Prove it then. Prove that the rotation of the planet causes the core to be as hot as it is, because otherwise it's a perpetual motion system.
No. Where's the energy loss?
Where's the energy loss going? No. What's putting the energy back in? Forget the energy loss. What's putting the energy back in?
Forget the energy loss. The energy loss is relevant because it makes it not a perpetual motion machine.
No. The energy loss is irrelevant because if whatever is lost, whatever that value is, it has to be replaced by something. And you're saying it's the rotation of the Earth. Miles Davis says it's the gravity and the pressure and the rotation of the Earth and the convection currents. He says that's what the cause is. I call bullshit because you can't prove it. You're saying it's the rotation of the Earth. That's part of what he said. He gave 4 reasons. You give him 1. Can you prove that it's the rotation of the Earth that fuels the core?
Yes, because there are model experiments to demonstrate this.
Evidence, please.
Do you know about the 3-meter experiment at the University of Maryland?
You can show me. Demonstrate it on screen.
All right, just give me a second. By the way, somebody in the chat just informed me the air pressure in that 8 miles deep hole is 6.375 bars. That is only air pressure.
6.37 bars. I mean, like, we would have to see the evidence of that and see does that jive with what that map says and stuff. We can come back to that.
All right. I'm currently finding the source. I just have to disable my ad blocker. So this is not. First of all, let me share my screen. This is not a scientific paper, obviously, but it's good enough to demonstrate it. If you want to look up the paper, I could find it for you. So what they've done in Maryland is they've taken a rotating, let me just disable the sound. This is a rotating sphere with about 2.5 to 3 meters diameter, right? And it contains 2 inner spheres. In the middle, there's a solid metal core, and around it, there's a layer of molten sodium. So sodium is a non-ferromagnetic metal.
But hang on, shouldn't you be using iron, not sodium?
You would have to melt the iron.
Yeah,
so that would be really fucking unpractical. Sodium melts at 97 or so degrees centigrade, so it's easy to do it.
Yeah, but does salt have a magnetic field?
Sodium.
Sodium, yeah.
No, it doesn't. No. It's diamagnetic, it doesn't do anything. So
how is that the same? That's not a comparable test.
Yes.
How?
Because the iron at that temperature, as you said, over the Curie temperature will also be diamagnetic.
No, it won't be. No, it won't be. That's the point.
Do you know what diamagnetic means?
Right.
What does what is diamagnetism? What is ferromagnetism?
That's two
What is
poles.
pyromagnetism? What is ferromagnetism and what is anti-ferromagnetism?
Right, you stuttered a lot there. What was the question?
All right, there are different types of magnetism, right? The most commonly known is ferromagnetism. That's the kind of magnetic behavior that iron, cobalt, and nickel show.
Alex, can you show me anywhere where spinning molten iron creates magnetic fields?
Iron, no. Sodium, yes.
Right, that's the problem. So show me something with iron.
You're moving the goalpost. In the beginning, we were at molten metals.
What do you mean? We're supposed to be comparing iron. Sodium is technically a metal, but it's not iron. So I'm asking you to demonstrate your point with iron, not with sodium. So can you show it with iron?
Why should I? If the magnetic properties are identical, sodium is conductive and sodium is non-ferromagnetic.
Because
That's more than enough.
the claimed point of the core of the Earth is not sodium. The claimed point of the core of the Earth is iron. So I
Yeah,
want you to know how iron-
good luck repeating that experiment with molten iron. I know
Exactly,
at least
that's the
two
point.
reasons. I know at least 2 reasons why that isn't a good idea.
Because it doesn't generate its own magnetic field would be one of them.
No, because it would probably melt through your floor.
That's a bullshit reason. Show how fluid iron can create a magnetic field in the way
I
that
can't.
you're showing. There you go.
I
So
can't because this
therefore it
experiment
doesn't feed
is hard
itself.
to do.
Therefore, it doesn't feed itself.
No. As
Right.
soon as we can show that
Alex?
rotating As
Yes
soon
or
as
no?
we can show that when you have a rotating setup like this with an inner sphere and an outer layer of molten metal, molten conductive metal.
Yeah, but
obviously.
I'm asking specifically for iron.
Yeah, and I said that's hard to do and probably not feasible in an experiment.
Then you can't prove that it does what you think it does then. Same as the pressure.
Do you agree that this experiment proves that metals can do that?
We're talking about iron.
That's not my question. Do you agree that metals can behave in this way when they're liquid?
I don't know about every single metal.
Yeah, metals in general, that doesn't mean everyone. In this case, it proves that sodium shows this behavior.
Yeah, but we're talking about iron. Does iron show this behavior?
Again, it's hard to demonstrate it.
So the answer would be no.
No, the answer is we don't know in this experiment.
Right.
But we can show that it's reasonable to assume it because
No.
this
In fact,
sodium-
it's a fact. Does
sodium show this behavior.
Alex, find me a source where it says that iron, in its molten form, can create its own magnetic field. Find me something.
As I said, I can't do it right now because I don't think an experiment like this exists.
So you can't assert it to be comparable then because it's reasonable.
I can assert it to be comparable because when we know that one metal that has set magnetic properties does it, another metal that shows the same magnetic properties might or will do it as well.
The inner core is supposed to be 7,000 to 10,000 degrees, whatever value it is. It goes beyond
5,700 Kelvin.
well 7,200 Celsius, just a number, but it's over and above the Curie point. Now you made the assertion that it was because of the pressure that was allowing it to go higher, but you're unable to prove it. I then showed that the iron, there's no evidence to support iron to create its own magnetic field. It requires an external source for the core to be magnetized. And I asked where was that external source coming from, because you've not got the evidence to show that it's coming from the rotation of the Earth caused by the movement of the fluid inside. So that's not the external source. So there has to be an external source, otherwise the core isn't magnetized.
Yeah, as said, the external source is the rotation directly.
Yeah, but we just demonstrated that it wasn't. You haven't got the evidence to prove that's true.
Yeah, again, as said, when one metal does it under that circumstances, it's reasonable to assume that another one does it as well.
Yeah, but that's a reasonable assumption. It's not proof.
Yeah, thanks for saying that it's a reasonable assumption. That helps me a lot.
Yeah, but it's not proof. So where is the magnetic core? Where is the magnetic force that's charging the magnetic center of the Earth? If you can't prove that there's an external magnetic source, I'm sorry, Alex, it loses its magnetism and it hasn't been replaced.
Yeah, that's because you don't understand how magnetism works.
Yeah, and you don't understand how evidence works.
Oh, for fuck's sake.